Very good. So let me start with the plan for today. So I will, of course, take as much time as I could to do the lecture today. So we will do lecture today with homework 4, and then we'll start the first 3 presentations. Okay, so that will be the plan. The first thing is last time I was reminded with Jasper and Michael. The package GLM did update itself. Okay, so the version that I was showing class was version 8, but if you look at the version right here, now it's version 10. Okay, so version 10. So I updated the R software, the version of the package, blah blah blah, and the graph that you should get. So this is the take-home project I talked about in class last time. Now the graph should look reversed. Okay, so now the graph should look reversed. In version 8, what we did was the graph was flipped around the y-axis. So the log of lambda is not negative, it goes from 0, 1, 2, 3, all the way to 6. However, here, for some reason, I'm not sure why, but for some reason they decided to reverse the ordering. So now instead of log of lambda going from small to large, from left to right, it will now go from small to large, from right to left, which is somewhat annoying, but it's still the exact same thing. Okay. So the first question is which one should we put on the take-home exams? Theoretically, it should be this one here, just because it's the newest version. But if you have the version 8, the other graph from package version 8, that's completely fine. Just make a note and saying like my version is version 8 is still correct. So that's the first question. Second question: which version of the graph will show up on the final exam? I updated my my computer over the weekends, and I changed the graph. So this version of the graph will show up on the final exam. Why? Because it's the newest. So we'll put the newest version of the graph on the exam. The next question to ask here is, what is the optimal lambda in the newer version? So this graph is version 10. The previous one we showed in lecture was version 8. In version 8, we said we select the lambda that's the smallest in absolute value. Here is exactly the same idea. So we select this guy right here, take the exponential, and that will be the optimal lambda. Okay, because here it's still the optimal lambda plus 1 standard deviation, but in the previous part, because we go from 0 to all the way to 6, plus standard deviation goes to the right. Here, because we're going in the opposite direction, plus standard deviation. So this one here is not the actual answer. The answer here is the one on the right. So to summarize what is happening, in version 10, the optimal lambda is along the right. Of course, you have to take an exponential there, don't forget, because it's the opposite lambda. And in version 8, the one's on the left. So which one will show up on the final exam? This one will show up. So it's along the right. The other thing to note here is you don't have to memorize version 8, version 10, blah, blah, blah. The thing here is, one of them is the optimal lambda, the other one is optimal lambda plus standard deviation. Standard deviation is always positive number. What that means is the thing plus standard deviation is going to be larger than the value itself. In version 8, because the numbers are positive, that means you go to the right. In version 10, right here, the negative value, that means you need to go to the left. So in this graph, this one on the left is not optimal lambda. The one on the right is not. Okay, and you can see the numbers how they decrease as you move towards the left, rather than version 8, they decrease as you move towards the right. So when you for log of lambda equals to 0, that's for lambda equals to 1. The model has 9 values, 9 parameters that are non-zero and fine. When the optimal lambda right here, which is log of lambda equals to around 0.8 or something like that, there will be 8 values that are non-zero in the model. And if log of lambda is equal to 6, then there will be 0 slopes that are equal to non-zero in the model. That means the model only consists of 2 numbers. And again, this is negative log of lambda, this is negative 6, so that's why log of lambda is 6. And don't forget the log. So take on the exam, the log of something to so contain you have to the exponential function. The value on the top are just simply having how many values in the model that are non-zero given the function. Good. So I hope that clarifies things because I know people have described pretty correctly. Version 8 for the take-home final is also just put a note there saying it's also correct. But for the final exam, we should look at for the in-person. Good. So I hope that clarifies things. We'll also see a graph like this during the review on Wednesday of next week. I'm pretty sure I could remember, but if not, remind me, okay, because it's going to show up on 5 minutes. Okay, so let's go back with the take-home exam and then finish that, right? Sorry, the take-home homework 4 because take-home exam is already covered. So other than the direction of the graph, I don't think anything else changed. The arrow was still at 10,000 something. So all the values should have stayed the same as last time. It's just the direction of the graph. Yes. Yeah, the error at least I got here was like 10.5 thousand, like 10532. So yeah, should be the same as before. I checked it a bit. They should be the same. But the only thing changes is the direction. Cool. Other questions? Good. Okay. So last time we were at the location of k nearest neighbors. So let me pull up my notes here. Okay. So I think last time we finished the function. So last time we introduced how to write our functions, and we finished the function where we were computing the distance between two vectors. Okay, so we required the stats package. We defined the function, and then we found the distance by using the dist command from the stats package. And then the whole thing was returned, and notice the absence of a space between return and the bracket. So that's very important. So today we continue with part B to actually do the k nearest neighbor regression. And as a review, I think I had the parameters listed on the notes from last time. So let me pull that up. Okay, so we define the four things: the data matrix, the response vector, the number of nearest neighbors, and the new data point. And what we were trying to do is for the new data point x new, we are trying to compute the distance between the x new to all the rows of the x matrix. So all the x's are the data matrix, each row is one data point. We're trying to compute the distance for this new observation towards each row of the x matrix, all the rows of my data matrix. And then I'm going to select the k smallest values. Okay, so that's the idea for doing so. And we said to do so, we first created this vector called distance, which is the same length as the number of the rows of my x. So that will record the distance between the new observation to each row of x. Okay. So the way we do the things is for this for loop where I goes from 1 to n, the distance of I could be computed using the vector function that we just wrote before, which is the toDistance. So toDistance is the function we wrote before. We put two vectors here. The first vector is going to be the ith row of the x matrix. So we go through the thing row by row, so ith row of the x matrix. And the second thing is going to be the new vector, right? Because we're trying to compute the distance between the new observation and the ith row of the data matrix. Okay, so that's why it's xi comma. Xi comma means the ith row of the x matrix, and x new is the vector that we're trying to find at the nearest neighbors x. And then we can put this, we can put a name for the distance, for example, Euclidean here. But if you don't like Euclidean, you can always change this. Very good. Okay. So once after this step, you will be we have computed all the distances between the new observation and every row of x. So there is only one more thing to do, and that is to sort the distances from small to large, and then select the k smallest location. Okay, that's the definition for k nearest neighbors. So let's go down. So now sort the distances and select the k smallest, select the k smallest line. So one way you can do the things to sort the values is to let's see, you can use the sort command. You could okay, yeah, you should use the order command. I mean, let's actually look at the example here so we can. So here we will use the order command for see order command for this, and we go from 0 to k. Yes. So now I order the distances from smallest to largest, and I select the ones which mark kth location of the ordered numerical matrix. What that means is I select the k smallest locations. So again, here what I'm doing is I'm selecting locations. Locations, i.e. the row index of x or the location of the y vector. They're the same. So the row indices of x. I'm selecting the k smallest locations according to the distance, and then I'm going to compute the mean value of their y values. Okay, so let's call this k nearest locations. K nearest locations equals to order this, and then the only thing left is to return the average y value of this location. So we return, notice the absence between the word return and the left bracket here. So we return the mean value of all the y vectors such that their locations are in the k nearest location. Okay, and that's it. And that's finished. Not too bad. It's not as long as it was expected. So again, to summarize on what has happened, we first, this is line 59 is like a Hopper function. So it basically just tells me what is the size of my sample. Then I create a distance vector of length n, where I compute the distance between the new observation and each row of my X matrix. Okay, by using the Hopper function to distance we wrote in class last time. So then we order the things, select the k smallest locations, and then return the average y values of those locations. And that's it. Okay? Any questions? Okay. So once we wrote the function, let me see if okay, so once we wrote the function, we should always try to see if the thing works. Oh, so let me copy this onto the slide. Yeah, that should be. So this is function. Okay, so now once we find the function, we should try to test if the function works as intended. So let's go to the assignment file. Part C should give us a new data point. Let's see. So part C gives us a new matrix, and this matrix is actually pretty simple. So the X matrix here X matrix here is just a vector that runs from the numbers of 1 to 5. So we can say this is matrix. The data goes from 1 to 5. The number of rows, because it's 5 by 1 matrix, so there are 5 rows. 1 column, number of columns equals to 1. And by row equals to true or false doesn't really matter because it's a size 1 matrix. So by row just means whether you fill the numbers according to row or according to column. Here there is only 1 column, so whether it's true or false, it doesn't matter. We'll just say false, so the matrix goes from 1 to 5. And then y vector is the vector that goes from 11 to 15, so 11 speech mark 15. K equals to 3, and the new observation equals to 2.1. Okay, new observation equals to 2.1. Now, let's just run the whole thing. Okay, so what we see here is the data matrix is in dimension 1, just for simplicity. The values are 1, 2, 3, 4, 5. The new X is 2.1. So the 3 closest values to 2.1 are the X values of 1, 2, and 3. Are the X values of 1, 2, 3. So if we look at what X is, this is the X matrix. We look at what Y is, this is a Y vector. 2.1 is closest to the values of 1, 2, 3 when K equals to 3. Therefore, the Y value, let's return returned by the function should be the average of 11, 12, and 13, which should be 12. Okay, so the function should return 12, and let's call the function to see if it does return 12. So k nearest neighbor regression. We put x here, y here, k here, and x mu here, and let's hope the function returns 12. Yeah, there you go. Okay, so that means the function is working as intended. If it doesn't return 12, then there's something wrong with the function, and we need to debug it. So let me copy this onto the slide. Good. So any questions regarding the testing of the function? Yes? Yeah, sure. Great. Any other questions? Okay, good. So last part, we'll apply this on one of the data sets. So we will go to the auto data set in the ISLR, the Introduction Statistical Learning package. And what we do is we get a new vehicle with 6 cylinders, 310 displacement, 140 horsepower, and 3,500 pound weight. And then using the 10 nearest neighbors, we want to do the k nearest neighbor prediction. Okay, k nearest neighbor prediction. So what we do here is so this will be in the auto data set prediction. So we require this guy. Here will be the auto data set with columns 2, 3, 4, and 5. So the columns 2, 3, 5. The Y response will be the first one, which is the miles per gallon. Okay, and then K equals to 10 because we have 10 nearest neighbors. The new one has 6, 310, 140, and 350. So x new is a vector in dimension 4 with the 4 numbers 6, 310, 140, and 3,500. So that's the x new. So we have the data matrix, the response vector, the k value, and also the new location. And now we should run k nearest neighbors regression with x, y, big X here, big X, y, k, and x mu, and let's hope for the best. Yeah, there you go. So the miles per gallon prediction should be 18.6. So it should be around 18 miles per gallon prediction according to k nearest neighbors. So let me just do the comments and then we'll post it onto the slides. This one are extracting or let's say defining data matrix, response vector, k value, and the new x location to make the prediction. So this one is part B. Good, and the value should be around 18.16. For this new. Good. Okay, so any questions on how we make the prediction here? Good, and that's it. That's the, oh, actually, I think the assignment has one more thing. We should compare this 18.16, which is the one predicted from k-nearest neighbors, to the one applied from least squares, like least squares regression. I'll just leave the least squares part as homework. It's like a two-liner, right? So LM command and then use the predict function where enter those four numbers inside a data frame object that you will get the result. So, two more lines to make the thing with least squares, which I'll leave as homework, but all the other parts are complete. So again, to kind of summarize what we have done in this assignment, we first talked about how to write our functions. Then we started to write a helper function which computes the distance between two vectors, any two vectors in any dimensions. After that, we used this helper function to write the k-nearest neighbors function. And the way we did that was once we had the new vector, we find the distance between this new vector to every row in the data matrix X. And then once I have that distance, which is stored in the distance vector, I sort the distance from small to large and select the k locations corresponding to the smallest k distances. By definition of k-nearest neighbors, those locations' y values will then be averaged and returned. So that's exactly what happened in this current chunk right here. So part B is the hardest part, which is the core of the assignment. After the core of the assignment, we always need to test whether the thing we have done is correct or not. So we had a very simple example to do a testing, and we done the testing, and the result was correct. It was what we were trying to expect. So that's the purpose for part C. And part D is to apply the thing to a real data set to make a prediction for the miles per gallon of a new car based on k-nearest neighbors. Okay, so and of course you should do the least squares also and compare the result with 18.16. So don't forget about that. Great. Any questions on this assignment, right? Yes.
Actually, by comparing, we mean like print out the value for the least squares and then just subtract it from the k-nearest neighbors.
Yeah, you could, or you could just say the value from k-nearest neighbors is 18, and the values from least squares is something, right? And then just list the two, and that's it. It doesn't have to be a detailed thing. You just say this guy's prediction is 18, the other prediction is this number, and that's it. Oh, gotcha. Because the two methods are the two methods does serve different advantages. The k-nearest neighbors is very relaxed on assumptions. It's focused on prediction only, and the least squares is more on like interpretation, higher dimensional things. So it is worth it to see like if there's any difference. Very good. Other. Okay, so that's the end of homework 4, and we also finished the take-home exam. Oh, remember, the take-home exam, yeah, this is the kind of the answer there, but the take-home exam is also a part F where you have to print out the answers. Okay, so don't forget, I purposely left out the part you should you should at least like that part is for homework. So there's also additional part for the take-home exam. So don't forget about that. Both of these assignments will be due on Wednesday of next week. Good. So we finished the